Import random import numpy as np import TensorFlow stf from TensorFlow.keras.models import sequential from TensorFlow.keras.layers import LSTM dense activation from TensorFlow.keras.optimizers import RMSprop. I'll break it down for you. Imagine you have a friend who loves playing with toys and wants to learn something new. Your friend has a bunch of toys, and each toy can do different things. Sometimes, your friend wants to make the toys do something specific, like a dance or a funny noise. To make the toys do what your friend wants, they need a plan. The plan tells your friend which toys to use and in what order to make something fun happen. Your friend has a special helper named TensorFlow. TensorFlow helps your friend with their plans for the toys. TensorFlow is like a smart assistant that knows how to use the toys in a special way. TensorFlow has a recipe book that tells your friend how to use the toys to make cool things. In this case, the recipe book is a set of instructions that tells TensorFlow how to use a special kind of toy called a neural network. A neural network is a special kind of toy that can learn and remember things. It's like a robot brain that learns from playing with toys and gets better at making plans. Inside the neural network, there are two types of toys called LSTM and dense. LSTM helps remember important things for a longer time, and dense helps make decisions based on what's remembered. Your friend uses numbers to tell the toys how to move and work together. TensorFlow helps your friend adjust these numbers to make the toys do exactly what they want. There's a special teacher named RMSprop who helps make sure the toys learn in a good way. RMSprop checks how well the toys are doing and suggests changes to help them get better at following the plans. Putting it all together. So, your friend uses TensorFlow, the recipe book, the neural network with LSTM and dense toys, numbers to tell the toys what to do, and the teacher RMSprop to make sure they learn well. After playing and learning, the toys can perform a cool show. Your friend has successfully used TensorFlow and the special toys to create something fun and exciting. In summary, TensorFlow and the neural network with LSTM and dense toys help your friend create awesome shows with their toys by following a recipe book and learning from a teacher named RMSprop. File path equals tf.keras.utils.get_file shakespeare.txt. We're asking our helper TensorFlow to go to the internet library again, find the special book written by Shakespeare, the same one as before, and bring it back. This time, we're saving it on our computer with the name shakespeare.txt. Text equals open, file path, rb.read.decode, encoding equals utf8.lower. Open, file path, rb.read. Imagine we have a magical tool that can open the special book, shakespeare.txt, and read all the words in it. .decode, encoding equals utf8. Sometimes, books can have a secret code, like a language only computers understand. This part helps translate that code into words that we can understand. .lower, in books, there are big and small letters. This part makes all the letters small, so everything is in the same size. It's like changing all the letters to be friends and play nicely together. Finally, we put all these readable and friendly words into a bag named text. So, text is like our own personal copy of the special book that we can read, play with, and explore whenever we want. Text equals text 300000:800000. Imagine our book has a lot of pages, and we previously chose a specific part to focus on. This line is like saying, now, let's only look at words from page 300,000 to page 800,000. So, text now only has the words from that specific part of the book. Characters equals sorted, set, text. Now that we have our selected part of the book, let's look at the different letters and symbols used. Set, text. This part is like making a list of all the unique things, letters and symbols we found in that part of the book. It's like listing all the different types of toys we have. Sorted, next, we organize these unique things, characters, in a specific order. It's like arranging our toys alphabetically or by size. Finally, we put this organized list of unique things, characters, into a bag called characters. So, characters is like a collection of all the different letters and symbols we found in that part of the book, neatly organized. char_to_index equals dict, C, I, for I, C in enumerate, characters. Now that we know what characters are in our selected part of the book, we want to give each character a number. This line is like saying, let's make a dictionary where each character is matched with a unique number. It's like giving each toy in our collection a special code or number so we can easily identify them. The enumerate function helps us go through the characters, and for each character, C, at position I, we create an entry in the dictionary where C is the key and I is the value. Index underscore to underscore char equals dict, I, C, for I, C in enumerate, characters. Similarly, now we want to go the other way around. We want to know which character corresponds to each number. This line is like saying, let's make another dictionary where each number is matched with a character. It's like having a list that tells us what toy each code or number represents. Again, the enumerate function helps us go through the characters, and for each character, C, at position I, we create an entry in the dictionary where I is the key and C is the value. SEQ underscore length equals 40. Imagine you want to read a book and understand it better. This line is like saying, I want to look at the story in chunks of 40 words at a time. So, SEQ underscore length is the size of each chunk or part of the story that we want to focus on. Step underscore size equals 3. Now, imagine you want to move along the story and keep reading. This line is like saying, after each chunk of 40 words, let's move 3 words ahead before looking at the next chunk. So, step underscore size is how much we move forward after each chunk. Sentences equals. We want to keep track of these chunks of 40 words. This line is like saying, I have an empty list named sentences where I'll put each chunk of 40 words as I read through the story. Next underscore characters equals. Additionally, we want to know what comes right after each chunk. This line is like saying, I have another empty list named next underscore characters where I'll put the word that comes right after each chunk of 40 words. For I in range, 0, len, text, SEQ underscore length, step underscore size. Imagine you have a big book, text, and you want to read it in chunks of 40 words, as defined by SEQ underscore length. This line is like saying, let's start from the beginning of the book and read in chunks of 40 words, moving 3 words at a time. The range, 0, len, text, SEQ underscore length, step underscore size, part helps us create a sequence of numbers, starting from 0, going up to the length of the book minus the chunk size, SEQ underscore length, and moving in steps of step underscore size. Sentences.append, text, I plus SEQ underscore length. As we read through the book in chunks, we want to remember each chunk. This line is like saying, I found a chunk of 40 words, starting at position I in the book, and I'm putting it into the sentences list. The text, I plus SEQ underscore length, part is how we grab a chunk from the book. It's like selecting a part of the story that is SEQ underscore length words long, starting from position I. Next underscore characters.append, text, I plus SEQ underscore length. We also want to know what comes right after each chunk. This line is like saying, I found a word that comes right after the chunk of 40 words, and I'm putting it into the next underscore characters list. The text, I plus SEQ underscore length, part is how we get the word right after the chunk. It's like finding the next word in the story after reading a chunk of 40 words. X equals np.zeros, len, sentences, SEQ underscore length, len, characters, type equals bool. Imagine we want to tell a computer about the patterns in our story. This line is like saying, I'm creating an empty grid, matrix, called X, where I'll put information about the characters in each chunk of 40 words. The size of this grid is determined by the length of our sentences list, how many chunks we have, the length of each chunk, SEQ underscore length, and the number of different characters we found, len, characters. np.zeros is a number py function that creates a matrix filled with zeros. It's like preparing a blank space to write down information. Y equals np.zeros, len, sentences, len, characters, type equals bool. Similarly, we want to tell the computer what comes right after each chunk. This line is like saying, I'm creating another empty grid, matrix, called Y, where I'll put information about the characters that come right after each chunk. The size of this grid is determined by the length of our sentences list, how many chunks we have, and the number of different characters we found, len, characters. Again, np.zeros is used to create a matrix filled with zeros. It's like preparing a blank space to write down more information. For I, sentence in enumerate, sentences. Imagine you have a list of chunks of the story, sentences. This line is like saying, let's go through each chunk, and for each chunk, we'll do something special. Enumerate, sentences, helps us go through each chunk and also keep track of its position in the list with the variable I. For T, character in enumerate, sentence. Now, for each chunk, we want to look at each character in that chunk. This line is like saying, for each chunk, let's go through each word, character, and for each word, we'll do something special. Enumerate, sentence, helps us go through each character in the chunk and keep track of its position with the variable T. X, I, T, char underscore to underscore index, character, equals 1. As we look at each character in each chunk, we want to mark something on our grid, X, to show the computer which characters are present in each position of the chunk. This line is like saying, in our grid X, at position, I, T, char underscore to underscore index, character, let's put a 1 to show that this character is present. Char underscore to underscore index, character, is a way of converting the character into the unique number we assigned to it earlier. This helps us mark the correct position in our grid. Y, I, char underscore to underscore index, next underscore characters, I, equals 1. Now, we want to do something similar for what comes right after each chunk. This line is like saying, in our other grid Y, at position, I, char underscore to underscore index, next underscore characters, I, let's put a 1 to show which character comes right after this chunk. Char underscore to underscore index, next underscore characters, I, is a way of converting the next character into the unique number we assigned to it earlier. This helps us mark the correct position in our Y grid. Model equals sequential. Imagine you want to build a robot brain to understand the story. This line is like saying, I'm creating a blank slate for the robot brain and I'll add different parts to it. Sequential means we're building the model layer by layer in a sequence. Model.add, LSTM, 128, input underscore shape set face seq underscore length, len, characters. Now, we want to add a special layer to the robot brain. This line is like saying, let's add a layer called LSTM to the brain. It's like a memory cell that helps the robot remember important things. 128 is the number of memory cells in this layer. Think of it as the size of the brain's memory. Input underscore shape set face seq underscore length, len, characters, tells the brain the size of the input it will receive. It's like saying, the brain should expect input in chunks of 40 words, seq underscore length, and each word can be one of the characters we found in the story. Model.add, dense, len, characters. Now, let's add another layer to the brain. This line is like saying, on top of the memory layer, let's add a dense layer. It helps the robot make decisions based on what it remembers. Len, characters, is the number of different characters we found in the story. It's like saying, consider all the different types of toys we have. Model.add, activation, softmax. Lastly, let's add a special function to the brain. This line is like saying, activate a function called softmax. It helps the robot make sense of its decisions and choose the most likely next character. Softmax is like a decision-making tool that makes sure the robot's choices add up to 1, like saying, I'm confident this is the next character, and the others have less chance. Model.compile, loss equals categorical underscore cross entropy, optimizer equals RMSprop, LR equals 0.01. Now that we've built our robot brain, we need to tell it how to learn and improve. This line is like saying, let's set up the learning process for the brain. Loss equals categorical underscore cross entropy is a way of measuring how far off the robot's predictions are from the correct answers. It's like giving the brain a score on how well it's doing. Optimizer equals RMSprop, LR equals 0.01 is like telling the brain how to adjust itself to do better. It's an optimization algorithm, RMSprop, that helps the brain learn by updating its memory and decision-making parts. LR equals 0.01 is a learning rate, which controls how big of steps the brain takes to learn. A smaller learning rate means smaller steps. Model.fit, x, y, batch underscore size equals 256, epochs equals 4. Now, we want to make the brain learn from our story. This line is like saying, let's feed the story chunks and their next characters to the brain, and let it learn from them. X is the input data, chunks of 40 words, and Y is the correct answers, next characters. Batch underscore size equals 256 means the brain doesn't learn from the entire story at once, but in smaller groups, batches, of 256 chunks. It's like teaching the brain in smaller steps to avoid overwhelming it. Epochs equals 4 is like saying, let's go through the entire story 4 times. It's like repeating the teaching process to make sure the brain gets better. Model.save, textgenerator.model. Once the brain has learned from the story, we want to save it for later. This line is like saying, let's store the brain on our computer as a file named textgenerator.model. So, textgenerator.model is like a snapshot of the brain's current state after learning from the story. Def sample, press, temperature equals 1.0 press equals np.array, press, .astype, float 64. Imagine the robot brain neural network has made predictions about the next character in the story. This line is like saying, let's take those predictions and get them ready for some special calculations. np.array, press, converts the predictions into a number py array, a type of data structure that's good for doing math. Now, we want to adjust the predictions to control how certain or uncertain the robot is about its choices. This line is like saying, let's make the robot more or less certain about its predictions based on the temperature. np.log, press, takes the natural logarithm of the predictions. This is a way of scaling down the predictions, and then we divide by the temperature. After adjusting the predictions, we want to bring them back to their original scale. This line is like saying, let's undo the scaling we did earlier. np.exp, press, calculates the exponential of each prediction, which helps to bring them back to a more natural scale. Preds equals exp_preds / np.sum exp_preds. Now, we want to make sure the predictions add up to 1. This line is like saying, let's normalize the predictions so that they represent probabilities. exp_preds / np.sum exp_preds divides each prediction by the sum of all predictions. This ensures that the predictions now represent probabilities, and they add up to 1. Probot equals np.random.multinomial 1 preds 1. Finally, we want to make a random choice based on these probabilities. This line is like saying, let's randomly choose one option based on the probabilities we calculated. np.random.multinomial 1 preds 1 performs a multinomial sampling. It's like tossing a bias die, where the bias is determined by the probabilities in preds. After making the random choice, we want to know which option was chosen. This line is like saying, let's find the index of the chosen option. np.argmax probar gives us the index, position, of the maximum value in the array probar, indicating which option was chosen randomly. In summary, the sample function takes the predictions from the neural network, adjusts them based on a temperature parameter, converts them into probabilities, makes a random choice, and returns the index of the chosen option. It's a way of introducing randomness and exploring different possibilities when generating text. Def generate_text, length, temperature. This line is defining a function named generate_text. It takes two parameters, length, the length of the text to generate, and temperature, a parameter that controls the randomness of the generated text. Start_index equals random.randint, 0, len, text, seq_length, 1. Now, we want to start generating text from a random position in our story. This line is like saying, let's randomly choose a starting point in the story, considering that we need to have enough words left for a complete chunk of 40 words, seq_length, random.randint, 0, len, text, seq_length, 1, generates a random number between 0 and the length of the story minus the length of a chunk. We are creating an empty string named generated to store the text we'll generate. Now, we want to take a chunk of 40 words, seq_length, starting from our randomly chosen position in the story. This line is like saying, let's get a chunk of words from the story based on our starting point. Text, start_index plus seq_length, slices the story to get a chunk of 40 words, starting from start_index. We are adding the chunk we just selected to our generated text. It's like saying, let's start our generated text with the chunk we picked from the story. In summary, this function sets up a starting point in the story, takes a chunk of 40 words from that point, and starts building the generated text with that chunk. The generated string will be the foundation for further text generation. For I in range, length. This line initiates a loop that will run length times. It's like saying, let's generate text for length iterations. X equals np.zeros, 1, seq underscore length, len, characters. For each iteration, we are creating an empty matrix X to represent the input for the neural network. It's like saying, I'm setting up a fresh input matrix for the neural network for each iteration. For T, character in enumerate, sentence. Now, for H word, character, in the current chunk of the generated text, sentence, we are going to do something special. Enumerate, sentence, helps us go through each character in the chunk and keep track of its position with the variable t. X, 0, t, char underscore to underscore index, character, equals 1. For each character in the chunk, we are updating our input matrix X. This line is like saying, in our input matrix X, at position, 0, t, char underscore to underscore index, character, let's put a 1 to show that this character is present. Char underscore to underscore index, character, is a way of converting the character into the unique number we assigned to it earlier. This helps us mark the correct position in our matrix. In summary, this loop goes through each character in the current chunk of the generated text, updates the input matrix X based on the presence of each character, and repeats this process for the specified number of iterations, length. This prepares the input data for the neural network during the text generation process. Predictions equals model.predict, x, verbose equals 0, 0. This line is using the trained neural network model to make predictions about the next character in the generated text. It's like saying, let's ask the robot brain what it thinks the next character should be based on the current input. Model.predict, x, verbose equals 0, is making predictions using the current input matrix X, and 0 is indexing into the predictions to get the array of predicted probabilities. Next underscore index equals sample, predictions, temperature, next underscore character equals index underscore to underscore char, next underscore index. Now, we are using the sample function, which we discussed earlier, to make a random choice based on the predicted probabilities. Temperature controls the randomness of the choice. It's like saying, let's make a decision about the next character, considering the uncertainty introduced by the temperature. We are converting the index of the chosen character back into the actual character using the index underscore to underscore char dictionary. It's like saying, now that we've made a decision, let's find out which character corresponds to that decision. Generated class equals next underscore character sentence equals sentence, 1, smiley face plus next underscore character. We are adding the chosen character to our generated text. It's like saying, let's build up our generated text with the characters we've decided on. We are updating the current chunk of the generated text, sentence, by removing the first character and adding the newly generated character at the end. It's like saying, let's slide our window of attention one step forward in the generated text. Finally, once we've gone through the loop for the specified number of iterations, we return the generated text. We are calling the generate underscore text function with a length of 100 characters and a temperature of 0.2 and printing the result. This is like saying, generate a short piece of text with a bit of randomness and show it to me.